dengue fever, and in general epidemic fatality, at least for this kind of small epidemics, they follow power law pretty well. Then we get the weird problem that the bigger ones seem to be misbehaving widely. And that's a problem because bigger can be very different. So it doesn't have to follow a nice mathematical rule, because the rules might be very different when you have an enormous epidemic and people start behaving differently. In general, of course, the classic one is the 1970 flu. So this is flu mortality year by year, and here you see the winter flu epidemic, and down and up here is the 1917 one. It's pretty scary. So this is the mortality rate of the United States, and this is that single epidemic. The really annoying thing is I haven't been able to get a good flu mortality data set to actually check whether it's a power law distribution. I have reasons to believe that it is, but I haven't got good data for it.
Anders?
Yeah.
Why do you think the mortality curve is going up again?
That one, I think that was partially the AIDS epidemic. Partially it might be that the American healthcare system is relatively crappy. And also a lot of it is probably just fluctuations.
The 57 and 68 flu pandemics don't really show it.
No. This one was so much bigger than all of the others. In general, I'm not that worried about new flu pandemics as many other people are because of that decline. But I might be wrong. I've been talking to various of epidemiologists in Oxford, and they have arguments why it could be wrong and bad. And that, of course, has to do with the different kinds of flu viruses, that we might be seeing the emergence of a new flu virus, which we haven't got immunity to, and might cause the kind of cytokine storm. So this is another demonstration how you can kind of lie with statistics. This is rather fresh data from the CDC. So this is when we've been checking how many positive isolates got sent to them, and they see their peaks. And it looks like it's the start of something very big here. But of course, this is stuff people send in to them from various hospitals to check. So given that we got so nervous about flu recently, especially about the porcine flu, they got sent a lot of extra samples. Of course we see an increase. But the important part here is the red stuff. We're actually seeing a new virus, which doesn't seem to be that terribly bad. But that might change. So it would be reassuring to know a bit more about the distribution of these kind of power laws. The reason for this, well, let me just show, well, this is dead in war, so I will show that. This is dead by their own government. And there are 3 different data sets here, because there is a tremendous amount of quarreling about how to actually measure this kind of dreary data. Rummel, who is a kind of big name on it, but also a bit more extreme than the others, he got this enormous black tome which I have got on my desk right now, and he got more data points than everything, but it's also going back further into time. In general, there seems to be a kind of power law distribution, but it might also be that we got a nice cutoff here, which would be extremely reassuring, because we're really talking about a lot of death here. The Chinese democides at least killed off a few tens of million people.
Is the Holocaust one of those people?
Yes, so it's up here somewhere. I don't know exactly where it is. So the really problematic thing, though, is that if you think about it, plotted as a time series, it seems that the size of the largest democide is increasing over time, because of course there are more people, and we're unfortunately getting better at killing each other. And that brings up this problem. We can't really be reassured that in the past we haven't had a war larger than this, or a democide larger than this, because we're actually changing the rules. So the important thing is the exponent of the power law, that's the slope in this diagram, has a lot of effect whether you're going to get these really extreme events. So if you have a pretty big exponent, like you actually the stock market fluctuations, and actually the estimated dead from asteroid, the big asteroid impacts, you actually get an average. It doesn't diverge, you even get a variance, everything's done. Down in this area, though, you don't have an average. You can get essentially, mathematically at least, arbitrarily big things. And in the past, it's not a good way of estimating how big it could be. Unfortunately, as you can see, most disasters I've been mentioning here tend to end up down here. There are some terrorist attacks in non-G7 countries which are up here, so there you would get some kind of average. So one way of kind of controlling this would be changing the system so you would change the exponent somehow. And in the case of a power grid, we can probably do a redesign, make it perhaps add firewalls or make sure that, well, if it fails, it's going to fail much more locally. It's a bit like aeroplanes where you set up things so that the entire wing can't be ripped apart, just an outer part or something. So in general, this is what I'm working on a paper about right now, so sorry for taking a lot of time about it. But power law seems to suggest that you can make estimates about some risks being actually potentially more serious, although we haven't seen any enormous instances yet. So I have plotted a lot of disasters together. So this is people killed, and this is estimated risk per year. And down here you get traffic accidents. Well, it's very reliable that a lot of people get killed, but it's always small groups. Then you get flooding up here. Flooding tends to cause the mid-size and so on. This is drought. And this might actually be a reason to think a bit more about climate change, whether it's anthropogenic or not. Climate fluctuations can be a very serious thing. There might be a hopeful break here, but we haven't got that much data points. But then we can combine this with my other data sets. So this is an even bigger scale here. And here we got the wars, and here we got the democide. And it seems that the outer envelope is actually the human-caused misery. So these are probably the ones we should be most concerned about. Yes, we should fix the flooding, for example. But if we fix the flooding but allow new Hitlers to come to power, that's actually going to be moved, because they're potentially much more risky for us. Especially since the real question is there anything that has any sensible chance to actually reach this dotted line, which would correspond to the total human population? It's pretty obvious that some of these ones got cut-offs, but we can't rely on that for wars, for example. So when you calculate based on this kind of model, the probability of getting a 6 billion killing war, it's 0.04% chance per year, which is about 40 millimorts. That's actually a pretty sizable thing. So this might be a problem we have been underestimating. Or rather, we have been channeling our efforts into particular things like nuclear disarmament, which is still a very sensible thing, without noting that we might want to figure out in the whole international systems to handle that kind of disasters. These are somewhat preliminary numbers. I'm still struggling a bit to get the database to work everything nicely together, so I'm probably going to put that on the web soon. Okay, so that was a bit about calculating the problem of disaster, where we have some experience, but we want to predict bigger things than have ever occurred before. This is actually a good caveat. This is a very good piece of statistics right after the pestilence, where you calculate the size of the next London pestilence. And the big problem was they didn't occur. But because we actually got healthcare better enough that we actually didn't get big pestilence epidemics. So we can change a lot of these rules, but we better make sure we change them in the right direction. So the really fun ones are, of course, the risk we actually have no real experience at all with. And I think a lot of us here in this room feel that Dilbert is right here. Yes, why not? That could happen. Should we worry about it? So in general, when you think about the stuff that has defined perhaps the last 20 years, like 9/11, the fall of the East Bloc and the internet, they're actually quite interesting phenomena, because they're afterwards, oh, it was obvious that it was going to happen. Before, it was definitely not obvious at all. And actually they changed the rules of the game, not just in the sense that our biases shifted and we suddenly started seeing networks everywhere or terrorists everywhere, or felt that, democracy will always triumph. But actually because we suggested a change in how we do things. Internet is pretty obvious in that sense, but also the whole concept of how political systems might shift and public power was really affected by the fall of East Bloc. And this suggests an interesting problem. Why didn't we predict it? Well, we can always find people who do predictions of the future, and some of them are always going to be right. But on the other hand, a lot of these ones involved relatively unlikely events coming together. But a lot of unlikely events are happening all the time. So it's actually not that strange that very unlikely events happen. So I noticed Nassim Taleb's book, The Black Swan, lying on the table in the pub. And he's been famously coining the term, a black swan, to denote this kind of totally unexpected event. But deep down, it's